Alright, so what we're going to be talking about today is in physics, we use energy diagrams and reference frames a lot. So this is like the stuff that we didn't cover in class today because we didn't have time. So I'm going to start with reference frames. So reference frames is just basically a point of view. So like, say if you're right here, right? Someone else is right adjacent to you. And then someone moves right between you guys. So basically, this guy might see him going to the right, but if I turn my page upside down, this guy might be seeing him moving to the left. So it's basically saying that motion is relative, and like right might be left for you, and it might be vice versa for another person. And also, like, sometimes someone can be moving very fast, like say like 1,000 meters per second, but they might be at rest. They might seem like, in their perspective, they're at rest because, say, if they're on a train or a plane, they don't feel like they're moving at all. But if someone were to observe that plane, they would actually see it being 1,000 meters a second. So the reason why reference frames are important is because we can manipulate reference frames however we want to make a physics problem more solvable. So like, in this case, we're talking about elastic collisions, in which kinetic energy is conserved, but as well as momentum. So, like, sometimes they might be both moving, about to hit each other. However, that would be more complex than one moving at, like, say 3 meters per second and another one just being at rest. It'd be much harder to find the two final velocities. So basically, what we can do is have this reference frame, let's just call it S, where in this case, one's moving at 3 and then one's moving at -4. We can have this reference frame move at -4 meters per second as well. So in that perspective, which we'll call it S prime, this object was moving at 0 meters per second. It's kind of like how if two people were running at the same speed, they're not moving like further than each other. Like they're basically in the same position as they're running, because they're not catching their eye, and because they're in a relatively same position in their perspective, that means there's no displacement, therefore there's no speed. And what we can do is we can actually use the Galilean transformation, which expresses v prime, which is the velocity of the object at this new reference frame S prime, and then we can, in the Galilean transformation, expresses that v prime is equal to v, which is initial velocity, so S prime, for like one of the objects at S, the original reference frame, and then minus capital V, which is the initial velocity of the object at rest in S prime. So what I mean by that is basically it's the initial velocity of the object that's going to be at rest at S prime in S. So like it would be better if I like gave you an example of this. So say if we have our example 3 and negative 4. So let's just call this V1 and then V2. So V1 prime would just be the initial velocity at S, so that's 3, and the minus the initial velocity at S for the one that's going to be at rest in the new reference frame. So that would just be 3 minus negative 4. And then you get 7 meters per second in this new S prime reference frame. So we could do the same thing with the second ball or object or whatever you want to call it. So negative 4 is an initial velocity at S, and then it is the object that's going to be at rest in S prime. So we just do 4 minus negative 4. So positive. So this is positive. So it would just give us 0 meters per second at S prime. This is quite useful because now you don't have to do more like complex analysis on elastic collisions, which is already complex enough when you actually do the derivation. I might actually have a video on the derivation of the predicting the final velocities of both objects if they have a perfectly elastic collision, as kinetic energy and momentum is conserved. I might have a separate video for that. But what that derivation is saying is that V1F is equal to 2m V1I, and then this is m1, over m1 plus m2. I mean, no, this is V2F, my bad. And this is V1I, and then V1F equals V1I multiplied by the quantity of m1 minus m2 over m1 plus m2. So this is what what I derived in class. So we can actually use the new reference frame to calculate V prime 2F and V1 prime F. Say if we were like given a mass and such. And then, but since it's in V prime and not V, the inertial reference frame, what we can actually do is take the equation again. So V prime equals V minus V. And then we can actually solve for the inertial reference frame. So once you get your V prime for both of these, you get V prime plus V equals V. So this would be so you'd be switching back to the original reference frame that the problem was presenting. So I will give you an example. So say if a 0.3 kg like ball is moving at, let's say, 4 meters per second, and then 0.6 kg ball is moving at -1 meters per second. So basically what you have to do is find the final velocities of both using perfectly elastic collisions. We're just assuming it's perfectly elastic, even though that is quite rare. So we can just make an S prime reference frame where it's moving at -1 meters per second. So let's just try to find our V prime in this new reference frame. So V1I prime equals, so we take the initial velocity of original, so 4, and minus -1, which is the object that's going to be at object's velocity originally in S, that's going to be in rest in S prime. So these two cancel and you get 5 meters per second in v1i prime. And then we already know that v2i prime would just be 0. So now what we're going to do is try to find v2f prime and v21f prime. So we can get our equations for that. So we can get v2f prime equals 2m1 v1i prime over m1 plus m2, and then v1f prime equals v1i prime times m1 minus m2 over m1 plus m2. So what we can do now is we can actually solve for v2f prime and v1f prime with the given information. So v2f prime equals 2 times 0.3 times v1i prime, which is 5 meters per second, and we get over 0.3 plus 0.6, and that should give you like a relatively like good answer. And then we can find v1f prime by taking v1fi, so which is 5, and then you have 0.3 minus 0.6 over 0.3 plus 0.6. So then taking what you have from v2f v2f prime and v1f prime, you just have to shift it back to the original reference frame. So you take this, so that's v2f prime, and set it equal to v2f minus v, and then that would just be, and then this would just be -1, right? Because that is the object at rest in S prime. So you just have v2f prime plus 1 equals v2f in the inertial reference frame. So, and then you can do the same thing with v1f prime and find v1f in the inertial reference frame. Alright, so the next thing I want to talk about is energy diagrams. So this might be quite new for anyone who's taken AP Physics 1 because they never covered it. But in AP Physics C they actually do cover it. So say if we were to have a graph, right? An energy versus position graph. So like say this is our X, and then this is our, let's just say U. Because for most of these graphs, they're gonna like plot the gravitational potential energy or elastic potential energy or both. Kinetic energy is not really included in it. So say if we were to have a graph like this, so basically, and then there would be, and because energy is conserved, there would be a total energy graph. I mean, not total energy graph, but a total energy line. So like, let's just say our total energy is right here. So basically, what this energy graph tells us is that there are points of stable and unstable equilibrium. So these 2 points are stable equilibrium, and then these 2 points are unstable equilibrium. And the reason this is because, like, pretend like this is on a hill, right? So like let's just draw a hill. And then right here is your point of unstable equilibrium. Let's just say there's a marble here. So if there's any amount of force to push this marble, it'll just keep going down and down and down and down, and like, it won't stop. So what it's trying to say is it'll leave whatever at a point of unstable equilibrium. Any amount of work done or any energy transferred is basically gonna like kick it out of the oscillation. It'll just keep going off in a different direction. However, say if we were to put this marble like right here, then if you push it a little bit, it's gonna go up and then it's gonna go down, because it's gonna go up with the initial velocity and then gravity's gonna pull it down, but then it'll have enough speed to go up again, and then gravity will pull it down again, and it'll just keep going up and down and up and down and up and down. And then basically what that means is that at points of stable equilibrium, there will be small oscillations with that particle. So this is basically what points of unstable equilibrium and stable equilibrium are. So another thing I wanted to cover is a thing called turning points. So this is basically whenever these two lines like the curve, the potential energy curve, and the total energy line intersect. So for like most terms, like an oscillation, that means it's gonna go back. Like say if you have a block on a spring, like right here, and it's at its turning point, that means it's moving here, that means it's ready to go the other way, because that's when it reaches its maximum like stretch length or compression length. So yeah, whenever it crosses the total energy line, that's just a turning point. So what you can actually do with this potential energy versus position graph is that you can actually find kinetic energy. Because remember, like total energy, like let me write it like right here. So total energy equals kinetic energy plus potential energy, right? So when you take when you subtract u on both sides, you can basically find the value of the kinetic energy at any point of this curve. So like say if this is like 2, 4, and then the total energy line has a value of 10. So this right here is 4 joules of potential energy, but then right here it would be 6 joules of kinetic energy. So like so just plug that in. So 10 minus 4 equals 6, right? So using this, we can actually like solve some of these problems and like find the kinetic energy and potential energy at any point. Also, it's good to know that potential energy and kinetic energy are inversely related. What I mean by this is, like say if you're in free fall, right? So you're losing, so basically when you're falling, you're losing altitude, like you're coming closer and closer to the ground. So what that means is your gravitational potential energy is going down. But since it's acceleration due to gravity, you're going to keep going faster and faster and faster. So that means your kinetic energy is going to go up. So we can actually find the points in which there is the the maximum speed or the maximum kinetic energy in a certain curve, and we actually can find when the object's at rest. So when we find the objects is at rest is basically the graph's turning point, because when the potential energy curve and the total energy line intersect, that means that all the potential energy is transferred to mechanical energy. Therefore, kinetic energy has to be 0. Therefore, speed has to equal 0. So with these turning points, you can basically see where it's at rest. So, yeah. And because potential energy and kinetic energy are inversely related, we could actually find the highest amount of kinetic energy by looking at the absolute minimum of the curve. So, like, say if we were to have this graph, it would be the lowest amount of potential energy is like 4 joules, right? So that means the highest amount of kinetic energy is 6 joules. And then, like, say if we're given a mass value, you can actually find the maximum speed on this potential energy curve. So something else I would like to go over is a little bit about work. So, like, for people in my class, we don't cover work until like a week or so, but it's nice to know to better understand this graph. So, work is defined as the change in energy, or we can write this as dE. So basically, and this is also the same as F times force times displacement, or the integral of force dx. So basically what we're doing is we're trying to find the slope of this graph. So let's do this like linearly. So we're taking the change in energy, the change in potential energy, which is force times displacement, over the change in position, which is delta x. So we basically get the slope of a potential energy curve with respect to position is just force, more specifically net force. And it's basically the same thing as du over dx equals force, right? So, and what that means is you can take the tangent line at any point in this graph and you can find the net force on that object. Alright, so okay, and something else I would like to mention is I would actually like to look at some energy diagrams of common things that we look at in physics. So, like, for example, free fall, it would just be a straight line because du over dx equals f, and then f is always constant in free fall because the acceleration due to gravity is constant, and then we're not losing any mass. But for like an object on a spring oscillating, it'll look like this, like du over dx equals f, but due to Hooke's law, f equals negative kx. And if you know an object oscillating on a spring, so like this, it's not always in the same position. The position varies because it goes back and then forth and then so on and so forth. And then like, so say in this scenario, so basically if we stretch this out, like if it's in motion, so basically like once we stretch it out, it's gonna actually come back, and it's gonna come closer to the equilibrium position, and then it's gonna overshoot and then try to compress and come closer to the wall, which is farther from the equilibrium position, and then it'll be at rest, and then it'll come back to the equilibrium position and then overshoot again. So basically, this is what it should look like, with this being the x equilibrium point. Alright, so here's an example of like an object like basically in equilibrium. So basically what you're doing is you're dropping a block of mass m, and then it compresses the spring a certain length. So you're basically trying to find the length of the compressed spring, or like the position where it's at when it's compressed. So there are two ways to solve this. One is just algebraically, and the other way is with calculus. So basically, because it's at equilibrium, the net force would equal 0. So that means the force of the spring and the force of gravity would have to equal each other, right? Because those are the only two forces that are being acted upon. So like if we were to draw a free body force diagram, this would be force of spring, and then this would be force of gravity. So basically what we can do is we can set these equal to each other. So force of spring due to Hooke's law is known as K times delta x, and that would equal mg. But what our delta x is our point of equilibrium, so x equilibrium minus the initial length, which is actually the length of the compressed spring. So we can just plug delta x in, so x equilibrium minus L naught equals mg. And what I can do is I could distribute this, so negative k x equilibrium minus LO times, plus, and then k here, and then equals mg. So what I can do is subtract KLO on both sides to get negative k x equilibrium equals mg minus KLO. And then what I can do is divide negative k on both sides to get x equilibrium of negative mg over k plus LO. So the way to solve this with calculus is, we know that du over dx equals the net force, and the net force at equilibrium is 0. So basically what we're trying to do is find the absolute minimum or maximum on the potential energy diagram curve of the total energy. So if we were to write the total energy equation, it'll just be mg times delta x, or no, not times delta x, but times x plus 1/2 k times delta x squared. So we know from here that delta x is x equilibrium minus LO squared. Not minus L squared, but minus LO. So U total equals mgx plus 1/2 k, and then x equilibrium minus LO squared. So because du over dx equals force, and what we're trying to find is where the force equals 0, we could just take the derivative with respect to position on both sides. So we get du total over dx equals, so this is known as a constant, but this goes away because it's, say if you have 2x, the derivative of that would just be 2. So it'd be mg, and then plus, and then we basically use the chain rule, so where we multiply by the, we multiply right here, so we multiply by 2, and then we subtract the variable, but then we multiply by the derivative in the inside, so plus k, so because the 2 and the 1/2 cancel out, and then x equilibrium minus LO, and then derivative of x equilibrium would just be 1, and then the minus LO would be 0 because it's a constant. So now what we could do is plug in the 0 right here, equals mg plus k x equilibrium minus LO, and then we could distribute mg plus k x equilibrium minus k LO, and we just get the exact same answer. So x equilibrium equals negative mg over k plus LO. One last thing I would like to cover is this problem right here. So we're given a potential energy diagram, and we know that we're given that kinetic energy equals 1 joule. What is the total energy equal? So, and this is at x equals 1. So like, let's just say this is 0 and then this is 2. So basically what we can do is we can get our formula TE equals U plus KE. So we know from the graph right here at x equals 1 that U equals 4, so TE equals 4, and then we're given that the kinetic energy at x equals 1 is 1 joule, so plus 1, and you get a total energy of 5 joules. So basically this is how you solve like basic energy diagrams. But I'll also ask you this, where is the maximum speed at? So the maximum speed will be at the point of the lowest kinetic energy, the lowest potential energy. So it'll just be right here at U equals 1. And because the total energy equals 5 joules, 5 joules equals 1 plus kinetic energy, and then kinetic energy would equal 4 joules. So just have a maximum kinetic energy of, 4 joules. And then say if you're given a mass like m equals like 2 kilograms, you could basically plug this into the formula Ke equals 1/2 mv squared, and then 4 equals 1/2 2v squared. So these cancel out, and then 4 equals v squared, and then v equals 2 meters per second, which is the maximum speed on the potential energy diagram. Alright, so that's basically all I have to cover. Thank you for listening.